Now let me show you the Jupyter notebook where actually I did all these things. So this is my NumPy, this is my Matplotlib, and also SciPy stat. So I'm importing my necessary libraries. I'm using the dog background, and this is the question. I want to let's say I toss a coin 5 times, and the probability of success of getting head is this. What is the PMF? And you want to calculate the probability of getting 3 head. So you specify n equal to 5. This is your x. This is the number of successes, and in this case, my p equal to 0.5, and so you calculate your probability and then print out your probability, and this gives me the probability right here. For each one of these are my corresponding probability. This is the probability of getting 0 head right here, and this one is the probability of getting 1 head, and likewise for the rest of them. I plot right here each one of them. So in this case I'm using bar plot, and you can see that bar plot looks exactly like the way the numbers are. So 0 would be this number right here. So if you come over here, probability of getting 0 is 0.03125. So probability of getting 0 would be 0.03125 right here, and likewise for the 1, 2, 3. Okay, then in this case, I'm also doing stem plot. So this is my stem plot right here. I'm just calling stem plot, and this is how it looks like with the stem plot. A little bit more visually, a little bit more aesthetic. I kind of like stem plot over bar plot. Okay, now let's say we have a different question. An assembly line produces machine parts, and the probability that a part is defective is, let's say, 20%. Now 3 parts are selected randomly and independent of each other. So what is the probability that exactly 2 parts are defective? Well, in this case, my number of trials I'm conducting is 3 because I'm selecting 3 parts. Okay, so in this case, my successes are going to be 0, 1, 2, 3. I can have I can have 0 success, 1 success, 2 success, 3 success. 3 success means that all 3 parts are defective. Okay, in this case, P equal to 0.2, calculate your probability right here. I print out the probabilities. So these are my probabilities. So in this case, probability of getting a 0 defect is 512, 0.512. Probability of getting 1 defect is this, and probability of getting 2 and 3 defect would be this number. This number is right here. Uh, so in this case, I do the plot again, and basically it's the same code. If you can look over here, my x and probabilities have changed. That's all. So when you plot it, you can see that your numbers are basically kind of like going down over here. So you can see that, yeah, 0.512, 0.384, 0.096, 0.008. Yeah, the numbers are going down. Okay, then I'm doing the stem plot. So in the stem plot, you can see your probabilities are basically going down. So probability of getting 0 is this number, probability of getting 1 is this, probability of getting 2, and probability of getting 3. Okay, let's say I define my probability as 0.1. I'm just experimenting now right now. So let's say I increase my number of trials. I say my number of trials is 40, and my probability of getting a success is 0.1. So if you have a small probability, your graph is going to be right skewed. So let's come over here. My x is going to be, let's say, possible number of success can be 0 success, 1 success, 2 success, all the way up to 40 successes. Okay, let me just put comma. This should be etc. All right, so my probability in this case is 0.1. I find my probabilities, then I print out the probabilities, and let's look at the probabilities right here. So in this case, let me just remove this. We are actually looking at all the probabilities. So let's look at probabilities right here. So when you look at the probabilities, you can see that your numbers, if you look at these numbers, this is 10 to the power minus 2. That's what it means. So this is small, small, then it increases over here. It increases, okay. It's increasing, increasing. Then it starts decreasing over here. You can see that's decreasing, 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 decreasing. Yeah, it keeps decreasing towards the end. So it increases somewhere over here a little bit, and then at the end it starts decreasing. All these numbers are very tiny. Okay, I'm going to plot them. So I plot that using stem plot, and you can see that initially it increases the probability of getting 0 success, 1 success, 2 success, 3, 4, 5. So it actually goes up a little bit, and then it starts coming down. Then it keeps going down. So in this case, you can see that your graph is, what skew is that? That would be right skewed, right skewed. And you can see that your graph actually is going in the right direction, skewed towards the right direction. Let's take a look at this one. In this case, p equal to 0.5. In this case, your graph is going to be symmetry. Same number of trials. I'm conducting 40 trial in this case. I'm specifying my p equal to 0.5. Find your probabilities, and I plot the probabilities right here. And you can see that if you plot this thing, you'll see a graph. This is pretty much symmetric. So yeah, 20. So you can see that number of the probability of getting 0 success would be a very small number. 1, 2, 3, 4, 5, and probability of getting 20. So it seems like probability of getting 20 is a very high success rate. It's very high chance. Okay, and then in this case, I'm actually using my p equal to 0.9. In other words, my probability of getting success is very high. It's 90%. Here, your graph is going to be left skewed. This is the characteristic of these graphs. So in this case, my number of experiment is 40, and my probability is 0.9. I compute the probability, plot the graph, and when you plot it, this is how it looks like. You can see that graph is left skewed in this direction. So this is the property of the graph that are using high probability. If you have a high probability, your graph is going to be left skewed. If you are using 50-50, it's going to be symmetric. If you're using, let's say this number, which is a small probability, is going to be right skewed.